Okay, so let's now do something slightly more complicated called RMSProp. So even the momentum itself, not many people use. RMSProp people often use it. So what is it? So the thing is, this learning rate, if you think about it, this is just a single number. And this scales all gradient dimensions equally with the same number, which can be bad because some dimensions might be big, some dimensions might be small, meaning some partial gradients may be super big, some gradients may be super small, and you're taking equal size steps. You're multiplying equal learning rates for all these gradient dimensions, which might not be ideal. So can we do a smarter scaling differently per each dimension? That's the basic idea. So we want to assign smaller learning rates for the sensitive weights and large learning rate for insensitive weights. How do you define sensitivity mathematically? So we're going to compute this G term, which is weighted average of the previous value and current gradient squared, to measure the size of the gradient, size of the partial derivatives in the gradient. And we're going to do inverse scaling. So if the size is large, then we're going to divide by gt plus epsilon square root. So don't worry about square root plus epsilon, just minor detail. The important thing is we're going to divide by, or multiply by the inverse of g. So if the partial derivative is very large, we're going to scale it down. If the partial derivative is very small, we're going to scale it up. Okay? Because we're dividing by the size. Because without this, say the first dimension here is 0.00001. Second dimension is like 100. And you multiply the same constant eta, then the first dimension is not going to move at all, while the second dimension moves quite a lot. But with the scaling, we're going to more or less match how much progress we make on first and second dimensions, because we divide by the size. So we're going to make equally sized updates for all dimensions. That's the basic idea. So we have kindly provided to the G dict. So your job now is to implement this. By the way, this is a vector, and this is Elmo-wise multiply. This is vector, and Elmo-wise multiply. If you're familiar with the Newton method, which is second order, which it realizes the second order Taylor approximation, this G is going to be a full matrix as opposed to a diagonal matrix. So vector, Elmo-wise vector can be equally thought of as multiplying a diagonal matrix of G to this vector, right? So this is diagonal matrix where only the diagonal entries has value and all zeros outside the diagonal, and the diagonals contain information about inverse of the size. of the partial derivative. And in practice, we cannot use the full second order or the full matrix here because of the size. Because we're going to work with billion parameter models, and in order to implement a full matrix here, we're going to have to store in the memory billion times billion parameters, which is infeasible. So this is a practical implementation of what Newton method does, which is scaling different partial derivatives differently based on the size. All done? Anyone finished? Okay. All right, so for the G dict, you do a weighted averaging with beta of the previous value and the new value, which is partial derivative squared. And for the descent direction, learning rate times the gradient, element-wise divide by square root of G plus some epsilon. Okay, that's RMSProp, and some people use it, but not very often. Almost everyone is going to use atom. And what's atom? It combines the idea of momentum and RMSProp. Okay, momentum includes some velocity, or the running average of the gradient, so that we can cope with very bad shallow local optimum and pass right through. Think about a ball rolling from a hill. If you have with small bumps, it's just going to pass through. And then we're also going to do gradient scaling here by dividing by the size of the gradient. So we make equal size jumps for all directions. So here's the equation. So momentum is the same. You compute the velocity, but here the velocity is some beta 2 times previous velocity and 1 minus beta 2 of the gradient squared. And here you take the momentum, divide by the velocity. And size of the beta, beta 1, beta 2, they're all going to be a very large number, 0.9. So how you incorporate the immediate gradient signal into your optimizer, it's going to be done in a very slow fashion, because it's going to pay more weight to the previous velocity and previous momentum. It's only going to add in 1 minus beta amount of the gradient information. Okay. And like in the momentum case, you take your in the momentum case, your descent direction was velocity, but now we're going to take the descent with the momentum divided by the velocity. Okay, so let's take some time to implement this. So here now we have dictionary for the momentum and dictionary for the velocity. This means what in terms of our memory overhead? How many times more? Right. So if our model parameter is 3 billion parameter model, sorry, 1 billion parameter, we need 3 billion. One for the theta, one for the momentum, one for the velocity. Is it still worth it? I think so. because everybody uses Atom for its stability. And about, I would say, 5 years ago, there was a group, a very famous machine learning group, who worked on reducing the memory by, as opposed to holding every momentum velocity in the memory, maybe compute this sparsely and maybe make updates in a very sparse fashion and do a very complicated math to show it works on convex objective. And people implemented the idea on neural networks, and it didn't work, and the field that just died. So this idea of Atom came up, I don't know, maybe 10 years ago, and practically nothing better has come out yet. Anyone finished? Anyone done? Need more time? Okay. Okay, so implementation quite simple, right? So you just implement whatever's written here. So take weighted average of the previous momentum, previous velocity, and do some scaling here. And your descent direction is learning rate times momentum divided by the velocity. And let's look at a visualization. I don't know if I can start from scratch. So this is an example running a gradient descent from this point with all these different optimizers. So you can see SGD got stuck in the saddle point here. Other methods like momentum can get out of this saddle point through momentum. And which one is the fastest? RMSProp, Atom, Eta, Delta, I think those are fastest. Okay, so let's take our transformer and apply gradient descent. So we're going to use a very small data set called a Shakespeare data set. I haven't run this cell yet. anyways, you guys can run it, right? All right. So the data set is already included in the folder so that you don't have to waste time downloading. And here we're going to use GPU. Okay. And we're going to try various optimizers that we just implemented together: SGD, Momentum, RMSProp, and Atom. And apply gradient descent. So we're going to load the data. So data is partitioned twofold with train and test. We're going to train the model, meaning we're going to apply gradient descent on all parameters in the transformer, all 6 blocks, and observe the loss over time. And also at the same time take the model and compute the loss on the previously unseen test data. So let's look at, you guys run it and see how long it takes. I haven't implemented it. Okay, so you guys run it, and I think it's going to take about 5 minutes or something like this. Have you guys executed the cell? Okay. So on my screen, it's comparing SGD, Momentum, RMSProp, Atom, and the training loss starts around 8.6 or something like that, and it drops over time to 7.7 for SGD, and to loss of 5.3, 5.4 for RMSProp and Atom. And same thing for test loss. So the test loss is smaller for RMSProp and Atom compared to SGD for the same number of descent steps. I have no idea how long this takes for you. Did it finish running or still running? How many iterations? 40? Okay, almost done then. When it's finished, make sure you run the plotting cell below. So if you look at the plot, it's going to visualize the loss over time for different optimizers. So let's look at the training loss. At the end, RMSProp and Atom converge to better points compared to Momentum and SGD. So what we have done is, last time we stacked 6 transformer modules on top of each other and completed the transformer. Today, we have backpropagated all the parameters in all transformer blocks and observed that the train loss can go down on some data that we downloaded together. And we observed it decreases the loss both on the training data and test data, so it doesn't overfit. So this test loss observes the log likelihood on the previously unseen test point. And next time, in order to make transformers work in real life practically, this is gonna never work. You really need to implement key value caching. Okay. So our current implementation is going to scale quadratically with respect to the sequence length, and it's completely infeasible. And we're going to make this feasible and bring down the complexity quite significantly next time.